Good afternoon.
Good afternoon.
All right, so how's everyone today?
Not the greatest.
I'm good.
All right. All right, just remember it's Wednesday. Oh, wait, it's Tuesday. Dang it. That's going to happen the whole day. Just kidding. I shouldn't joke around like that. But all right, let's see. Everyone's there at Mogollon. Everyone's there at Winslow and St. John's. Who's missing today?
We're all here.
We're all there? Okay. Wonderful. Okay, so let's just double check really quick. Okay, so I've got quizzes tomorrow on 2.4 and 2.5. And let's just verify that. Okay, so Jordan and Hannah at 10:15, and let's see, the rest of Mogollon at 1:50 for the quizzes. All right, St. John's after class.
Would we be able to do them at 1:30, or do you want us to
from
just do...
from 1:30 to 2:30?
Or wait, 2:30? No, wait. What time does...
What?
Okay, well, class starts at 2:50. You want me to do it from 1:50 to 2:50?
Yes.
Yeah.
All right, let's do that then. So from 1:50 to 2:50. Okay, and then Winslow right after class. Did I say that? Just right after class. Yes. I think I saw yes. No.
Can we do it? Can we do it at 8:45
Sure.
and 9:45 tomorrow?
Sure.
Okay.
Okay. 8:45 to 9:45. We'll do it. And so it'll just be those two quizzes, 2.4 and 2.5. We might finish 2.6 today, but we're not going to do the quiz on that yet. Okay? All right. So any other questions, comments, concerns? Okay. Well, let's see, did I write down where we were? No. Let's see if I marked it. Oh, here we go. Okay, so practice 4. So if you want to get that out, we'll start there. Okay. All right. So we were going to try to find this limit as x approaches negative infinity for x is less of x cubed minus 2 over absolute value of x cubed plus 1 for x is less than 0. Okay. So yesterday, what we talked about with this type of problem is kind of the first thing you have to do is get rid of the absolute value. Okay? So what are we going to replace the absolute value of x with if x is less than 0?
Negative x.
Negative x. So this is going to be like negative x cubed. Okay? All right, so next, for limits that approach infinity or negative infinity, kind of the shortcut that we talked about is using the ideas from pre-calculus, where a limit as x approaches infinity or negative infinity is like finding the horizontal asymptote. Okay? So to find the horizontal asymptote, we compare the powers. So since the powers are the same, then what's the limit going to be for this problem? If the powers tie, it's the same as what the horizontal asymptote would be.
Is it -2?
Nope.
-1.
-1. Because, see, let's go back to the screen with the horizontal asymptotes. Okay? With the horizontal asymptote, if the powers are the same, then the horizontal asymptote is y equals a over b, where a and b are the leading coefficient. And so that's going to be the limit as x approaches either positive or negative infinity. And so with this, it's since the powers tie, the leading coefficient is 1 over -1, and so it's going to be -1. Okay? Now look how different, if x were approaching positive infinity, the horizontal asymptote or the limit would be +1, because then you just drop the absolute value, and so you'd get 1 over 1. But when x is approaching negative infinity, the horizontal asymptote or the limit is -1. Okay? So you do kind of have to, it does make a difference whether x is approaching infinity or negative infinity. Okay? All right, any questions on this one? All right. All right, next. Limits with the argument 1 over x. Okay? Sometimes if it's difficult to do a limit where the variable is in the denominator, then one little algebra trick that you can do is introduce a new variable that's the reciprocal. So like say t, which is 1 over x. So that would mean 1 over t is equal to x. All right, so let me give you an example of something like this. So, now remember that this was the limit that you memorized. No, it's not. No, it's not. Okay, these two are equivalent statements. Okay, we actually haven't calculated the limit yet. So let's say if we had the limit as x approaches infinity of the sine of 1 over infinity, then that's the same thing as if you say t is the reciprocal of x, then you can take the reciprocal of that, and then as x approaches infinity, that's the same thing as t approaching 0. Okay, and so now it might be a little more clear in your mind what's happening here. See, this is saying, okay, now the sine, as t approaches 0, the sine is going to approach what number? 1. That's right. 1. The sine of... Oh, because sine goes through the origin. I'm thinking the cosine. Sorry. So the sine of 0 is 0. The sine goes through the origin. So as t goes to 0, the sine goes to 0. Okay? So just see if you can kind of what your reasoning is. So you might want to do the variable switch. You might see if you can plug in infinity or negative infinity and sort of reason out what you think the answer is there. Okay? Just kind of see what you can do for that problem. All right, so Nathan, what do you think?
0.
0. Okay, I think that's a good guess. Let's see. Okay, so if you could look at as x approaches infinity and negative infinity separately. Okay, and we want to see if we end up with the same answer here. Okay, because it's very, like it showed on the last problem, that it's possible we could get two different answers here. So we got to be a little careful. All right. Now, if we do that little variable swap thing, so as x approaches infinity, that's the same thing as t approaching 0 from the right. X approaching negative infinity is the same as t approaching 0 from the left. So this is the same thing as, so 1 over t times sine of t is the same thing as sine t over t. And that is the one limit I asked you to memorize, that answer is 1. So what is happening here is, here's this crazy limit here, this crazy function, but as x is approaching infinity or negative infinity, the y value approaches 1. Okay, so now, if on any limit like this, let's say if this is on a test and you don't think to do that variable swap thing, that's okay. But what you want to do then is, if you're not sure about a limit, then you want to make a graph or a table. See, as x approaches 0 here, the original question is x is approaching infinity or negative infinity. But if the question was as x approaches 0, see, that might be an oscillating discontinuity. You might not be able to tell. But as x is approaching infinity, see, the y value is leveling off here at 1. So either from the graph or the table that I would want you to do it. So anyway, I was just trying to show you how one where this variable switch, looking at the reciprocal, might be helpful. But if you get stuck, just use the graph. Okay? All right, parts 6 and 7 together. The sandwich theorem and horizontal asymptotes. While the sandwich theorem holds, you must be sure that as x approaches infinity, that f of x stays between the outer functions. So what that means is that, like, if we're saying that that f of x is between g of x and h of x, okay? So let's say this black function here is g of x, and this one is h of x, okay? See, we could say if they come together at this point, then this blue function, we could tell what the limit is of that, because it's going to be the same as these other two. But see how the green function goes outside the boundaries? If it goes outside the boundaries, you cannot use the sandwich theorem to state that limit. Okay? So you got to be a little careful to make sure that your function stays inside the boundary functions. Okay? All right. So let's say that I want to find the limit of 2 plus sine x over x as x approaches infinity or negative infinity. Okay? So I know that the sine is between -1 and 1. So that means that sine x over x is going to be between 0 and 1 over x. Okay? So you can use these two as your boundary functions. So as x approaches infinity, 0 is just going to be 0. That's a constant. Okay, but the limit of 1 over x, well, as x approaches infinity, a constant over infinity is going to go to what? We did that yesterday. Constant over infinity is going to go to what limit?
1.
Nope.
0.
Zero.
It'll go to 0. So if this goes to 0 and this goes to 0, then this limit, as x approaches infinity, this of absolute value of sine x over x is going to be 0. Okay? Now, again, this is the limit. This is the limit that we've memorized, that I expect you to know. But this is as x approaches 0. Just because you see sine x over x, don't just rush to the idea that, oh, this has got to be 1. Because as x approaches infinity, this is going to go to 0. Okay? So, again, here's the graph of sine x over x. You might remember that. So as x is approaching 0, the y value here is 1. But as x is approaching infinity, the y value goes to 0. Okay? So, then if this limit is 0, then the limit of 2 plus 0, that's going to go to 2. So what I did is I used the sandwich theorem to get this right here. So I was actually, my original question would be, find the limit, say as x approaches infinity, of 2 plus sine x over x. And so then what I'm doing is using the sandwich theorem to figure out that this goes to 0. And so I have 2 plus 0 is going to be 2. Okay. All right. So let's see if you can do this one. The limit as x approaches 0 from the right of x times, now this is the greatest integer in 1 over x. Okay. Now, the hint that I'm giving you here is that x times the greatest integer of 1 over x lives between these two. Okay? All right, so Hannah Z, when you've got it.
I'm lost.
Okay? All right, so when you see this compound inequality, then what you think is that you're going to use the sandwich theorem on this. Okay? So with the sandwich theorem, if this function, see this is too complicated to plug in. X times the greatest integer of x. We don't really know how to do that. I mean, maybe you do. Maybe you could figure it out. But here, it's like as x approaches 0, see, if you tried plugging it in, you'd get 0 times infinity. Okay? All right, that's a bad thing. When you get 0 times infinity, you have no idea. 0 times infinity gives you nothing. It's not, because you don't know if it's closer to 0, you'd get 0. If it's closer to, it's just confusing to even think about 0 times infinity. All right? So the idea is that you're using the sandwich theorem. Okay? So you're going to, let's see. Actually, I don't think you even need to do the reciprocal. Okay? you can just say, what's the limit of this as x approaches 0 from the right? What's the limit of 1 minus x as x approaches 0? Hannah, what would it be? Just that little piece. 1 minus x.
1.
1. And then what's the limit of 1?
1.
1. Because if it's just a constant, there's nothing to plug in. Okay? So if this function lives between these two, and this limit is 1, and this limit is 1, then the limit of the function we want is 1. Does that make sense? So that's what the sandwich theorem is all about, is how we can use those outer functions and not even have to deal with this complicated mess in the middle. Okay? All right. So infinity times 0, that gives us problems. And then here's another one that gives us problems, is if we end up with infinity minus infinity. Okay? So if you end up with infinity minus infinity, then you try to multiply the numerator and the denominator by the conjugate. If you can. That's just another trick. Okay? So the conjugate. So let's say we had this. Find the limit as x approaches infinity of this. So if we try to plug in infinity, we're going to get infinity minus, well, infinity squared plus 16 is infinity. Square root of infinity is infinity. So we're going to get infinity minus infinity. That's no good. Okay? So then in this case, you try multiplying numerator and denominator by the conjugate. So here, x minus the radical. The conjugate is x plus the radical. Okay? Now, and then you just leave it in the denominator because it's just like times 1. And so then when you multiply the conjugate, see, you'll get x times x is x squared minus, and then the middle terms will cancel. And so then you get the radical times the radical will come out of the radical. The denominator, don't even multiply it out. It's just 1 times that, so just put that down there. But now what's going to happen here is stuff is going to cancel. The x squareds are going to cancel. Okay, so I'm going to get negative 16 over the denominator. Well, now if I plug in infinity here, I get infinity plus infinity, which is infinity. So if I have a negative constant over infinity, or any constant over infinity, what is that going to approach?
1.
No.
I got.
Okay. Here's how. Look. Okay. I remember missing a lot of these when I was first learning this rule. Okay. So on a test, if you're not sure, then make a little table. So put like negative 16 over, and then have the number get increasingly big, like it's going to infinity. So negative 16 over 100, negative 16 over 1,000, negative 16 over 1,000,000, negative 16 over 1,000,000,000. And what is that approaching? Not 1, but
0.
0. Okay? So any constant over infinity is going to go to 0. And so that would be the answer. Okay? All right, so go ahead and try practice 8. Okay, so Hannah, what do we multiply by? Hannah Z. What do we multiply by?
The conjugate.
The conjugate.
So what is the conjugate here?
X plus minus 9 squared minus x plus 4 squared.
Okay, square root, you mean. Okay. So we're going to multiply numerator and denominator by that. Okay. All right, so Skylar, when you've got the final answer, let us know.
Is it 0?
Is it 0? It is 0. Great job. Okay. All right. So, when we do these problems, it reminds me of that Shakespeare play, Much Ado About Nothing. So you spend a lot of work to get 0 is your answer. So would anyone like me to go through it?
Yeah, can we please go through it?
Sure. Okay. So you multiply by the conjugate, and so radical times radical x plus 9 times radical x plus 9 is just x plus 9. Minus. Okay, the outer and the inner products will cancel. And so you get radical x plus 4 times radical x plus 4 is just x plus 4. And then the denominator don't multiply anything. Okay, so then when you simplify, to drop the parentheses, you get x plus 9. Distribute the negative, and you get negative x minus 4. So the x's cancel, and 9 minus 4 is 5. So now when you try to plug in infinity again, you're going to get 5 over infinity, and any constant over infinity is going to go to 0. All right? Any questions on that?
I hate you.
Yeah?
No, sorry, I didn't mean to turn the mic on.
Oh, okay. I just want to make sure I'm not missing a question or something. Okay, next, oblique asymptotes. So again, this is a pre-calculus concept here. If the power of the numerator of a rational function is greater than the power of the denominator, there is no horizontal asymptote, but a slant or oblique asymptote. Okay? Most trig books call it a slant asymptote, but your calculus book calls it an oblique asymptote. It's the same thing. Okay? To find a slant asymptote, use polynomial division, but ignore the remainder. Okay? So, let's review polynomial division. All right, so let's say if I'm trying to find the slant asymptote for this, okay, or oblique asymptote. See how the power is bigger in the numerator. So when that happens, there's no horizontal asymptote, but instead there's an oblique asymptote. So you set up your polynomial division, you put your numerator underneath the quotient bar, and remember in polynomial division, your polynomials must be in descending order, and you have to have all your placeholders. So here you have x squared plus 0x minus 3, and then your divisor goes on the outside. Now you look at your leading terms. So 2x, what times 2x would give you x squared? Now this is where it's different than in your pre-calc class. Because in pre-calculus, we never did you dirty like this, where you had to deal with fractions. Okay? But what times 2x would give you x squared?
1/2 x.
1/2 x. See, you never had that. You never had a problem like that in trig. Okay? So now you multiply through 1/2 x times 2x is x squared. 1/2 x times -4 is -2x. Change the signs, boom, boom. And again, I would recommend that you use a pen and a pencil or 2 colors of pen when you're going through and changing the signs, because otherwise it's hard to recover. It's hard to figure out what you're doing. All right, so now you subtract x squared minus x squared. That cancels. 0x plus 2x is 2x. You bring down the -3. So now you look at the leading terms again. What times 2x is 2x? 1. So you put a +1 up there, and you multiply through, and you get 2x minus 4. Change the signs, boom, boom. This goes to 0, this goes to 1. -3 plus 4 is 1. But you really don't care, because that's the remainder. And in this, you ignore the remainder. So this quotient right up here, y equals that, is the slant or oblique asymptote. And so it is x over 2 plus 1, or 1/2 x plus 1. So that is the equation of this oblique asymptote. Okay? And so that's a guide to help you know where the graph goes. Okay? Now, as x approaches infinity, as the graph hugs along this oblique asymptote, it's still rising without bound. And so it's going to go to infinity. And then as x approaches negative infinity, see, then the y value is going to approach negative infinity on that vertical asymptote. Okay? So to find the slant or vertical asymptote, you use the polynomial division. All right, so go ahead and you try practice 9, please. All right, so Denon, when you've got it.
X plus 2.
Okay, so you want to say y equals for the oblique. So y equals x plus 2. Great job. Okay. Now, in this one, since you are dividing just by x plus or minus a number, you could also use synthetic division to get that. Would anyone like me to review synthetic division?
Yes, please.
Okay, so with synthetic division, you put the, okay, so we have x squared plus 0x minus 9. So you have 1, 0, negative 9 across the top. So you still need your placeholders. And then if you're dividing by x minus 2, so the opposite of this number goes in the magic box over here too. All right, and so then you just bring down the first number, and then you multiply. 1 times 2 is 2, and add. Multiply, 2 times 2 is 4, and add. So the last number is the remainder, so you ignore that. And so then you have 2, and then this is your coefficient of x. So it's still y equals x plus 2. We get the same answer, and just ignore the remainder for the oblique asymptote. So this y equals x plus 2, that's this slanted line. That's the oblique asymptote. All right, any questions on that? All right, so good job. All right, part 10, infinite limits. When we say a limit equals either infinity or negative infinity, remember, we are not saying the limit exists. It just helps us to know that the difference between a function that goes to infinity, see, this would be a function that goes to infinity, or a function that goes to negative infinity, or if like here we had a function where the left and the right hand limits don't exist and the limit doesn't exist, it helps us to know the difference between these situations. But in all these cases, the limit doesn't exist. But if we know like that it goes to infinity or negative infinity, that's better than just saying it doesn't exist. All right, so now, if just looking at this picture, as x approaches 1, from the left and from the right, it's not going to match up, because the left-hand limit, as x approaches 1 from the left, the function's going to negative infinity. So here, as x approaches 1 from the right, the function approaches positive infinity. So that means in general, the limit is not going to exist. Okay, so that's kind of how you do it with a graph. Now, you can also sort of reason it through without a graph, so without putting it in your calculator. So let's kind of go through that. And then you can do it whichever way you feel more comfortable, either putting it in your calculator with a graph or just sort of looking at it and reasoning it through. So like here, you say, well, see, if as x approaches 1, that would give me a constant over infinity. So that means the answer, a constant over 0. So that means the answer is either going to be infinity or negative infinity. And that's where you have to look at the signs. This is positive. Value slightly less than 1 would be like 0.9. So that would be negative. Positive divided by negative would be negative. Same thing here. If you plug in 1, you'd get a constant over 0. So the answer is either infinity or negative infinity. So then you think, okay, now a number slightly bigger than 1 would be 1.1. So that's positive over a positive, so positive infinity. And then since these don't match, it does not exist. Okay? All right, so let's have you do practice 10. And you can either put it in your calculator and look at the graph, or you can just sort of reason it through, thinking about the left-hand limit and the right-hand limit. All right, so Joey, when you've got it.
So you end up with 1 over 0, which is the limit doesn't exist, right?
So, no, 1 over 0, and a constant over 0, it's going to go to either infinity or negative infinity.
Infinity.
All right, so your guess is infinity, and the answer is from the left, when you plug in values slightly less than 3, whoops, it's going to go to, come on, it's going to go to infinity. From the right, it's also going to go to infinity because it's squared. So you're going to have a positive over a positive in both cases. So that means the limit in general is going to be infinity. Okay? All right, now, different problem. Well, first of all, is there any questions on that? All right, now let's go back to where we started. What would be the limit of this function as x approaches infinity? Anybody tell me? What's the limit of the function as x approaches infinity?
0.
0. Why? Why? Did you look at the graph? What made you know that it's 0?
Because, like, if you plug in a bigger number, then it's going to be a bigger.
Okay.
It's gonna
Bigger denominator. So, or if when x is approaching infinity, that's where you can compare the powers. And so if the power is bigger in the denominator, the answer is 0. Okay? All right. Well, good. Okay, so if a function approaches infinity as x approaches a number from one side and negative infinity as it approaches from the other, we say that the limit does not exist. So that would be where on, let's say on a vertical asymptote, if the graph goes up on one side of the vertical asymptote and down on the other, then we say the limit doesn't exist. Because infinity and negative infinity are not the same. All right, two-sided limits. If a function approaches infinity from each side of the vertical asymptote, we say that the function approaches infinity. So if you have a vertical asymptote and both sides go up, then we say the limit is infinity. So even though the function is discontinuous, it still can have a limit at infinity. All right, so like this one, as x approaches 0 from the left, it goes to infinity. As x approaches 0 from the right, it goes to infinity. So we would say the limit in general is infinity. Okay? All right, so see if you can do that one. So either reason it through or put it in your calculator. All right, Aiden.
It goes to negative infinity.
It goes to negative infinity. Very good. So both sides go to negative infinity. All right. Any questions? All right. Well, let's just have you write this down and then we'll quit. So rational functions can behave in various ways near the vertical asymptote. So that's kind of what we've been talking about. The function could go to infinity, negative infinity, or not exist. All right, so that's a good place to stop. We'll pick it up with part 12. I told you this lesson never ends, it seems like. So we'll pick it up from there tomorrow. Any questions, comments, concerns before we call it? All right. Thanks, you guys. You're an awesome class. Appreciate your hard work. Good luck on your quizzes tomorrow. And we'll see you then. See you tomorrow.